Hello dear friends, welcome to the lecture of Laplace Transform. In this lecture, we shall study Laplace Transform of Derivatives and Laplace Transform of Integral. These are the theorems on Laplace Transform and are useful to evaluate Laplace Transform of different type of functions. First, we shall see Laplace Transform of Derivatives, which is theorem 6 I have written here. If L of f of t is equal to small f of s, this is usual notation, then Laplace transform of nth derivative of f at t is equal to s to the power n fs minus s to the n minus 1 f of 0 minus s to the n minus 2 f dash of 0 minus so on s f, this is n minus second derivative of f at 0 minus n minus first derivative of f at 0. Here we should note the notation for the derivative. This notation, nth derivative of f is written like this, f and nth derivative is written in bracket, which stands for nth derivative of f, dnf by dtn. So this is the result that we shall first prove, and for the proof we shall consider here it is given Laplace transform of f of t is equal to fs. So that is the usual notation, let. And by definition this is fs and this is integral 0 to infinity e power minus st f of t dt. We may assume this as 1. Or yes, or this is usual definition, need not require a reference. And now we are using this definition, we shall first find out the Laplace transform of first order derivative, then Laplace transform of second order derivative, and observe the result, and accordingly these results we can write the Laplace transform of nth derivative of f. So we have, this is by definition, Laplace transform of f dash of t is equal to, see, Laplace transform of f of t has this definition, integral 0 to infinity etc. And similarly it will be integral 0 to infinity, this is kernel e to the power minus st, and instead of f here is f dash, so f dash t dt. Now this integral is a product of these two functions and we shall evaluate this by parts. And while evaluating it by parts, see, second function we take this as same f dash of t instead. So usually according to the rule LIAT exponential should be the second, but here we shall keep this as the second function because it is the derivative of f and we want to integrate the second function in the rule of integration by parts. So its integration is easy. Integration of this derivative is the original function because these are integration and derivative are inverse of each other. So integration of f dash t will be f of t, and therefore we integrate by parts. Integrating by parts, we get, see, the left side is Laplace transform of f dash of t is equal to, and first function e to the power negative st, integration of second, I am writing the rule of integration by part directly. First function integration of second, what is integration of f dash t, which is f of t, and the limits I shall put over this bracket 0 to infinity minus integral 0 to infinity derivative of the first with respect to t e power minus st. So that is e power minus st into derivative of minus st with respect to t, that is minus s. So minus s e power minus st is the derivative of e power minus st, you note this. And again the integration of second, that is integration of f dash t, which is f of t dt. So this is the rule of integration by parts we have used. And further this is equal to, Now put the upper limit here, this becomes e power negative infinity and this tends to 0. So because of this term is 0, so function's value at infinity, whatever it may be, this term becomes 0. 0 into this is 0 minus, and now put the lower limit t as 0. These are the limits of t, e power 0, and e power 0 is 1. So that is e power 0 and f of 0, f at 0. So this much is the evaluation of the term, first term. Now next is, here you see the integration is with respect to t, and therefore s can be written outside the integral, and this negative of negative becomes positive. S integral 0 to infinity e power minus st f of t dt, or this is equal to, now you see this is 1, e power 0 is 1, so it is minus f of 0 and plus s. What is this value? It is here, integral 0 to infinity e power minus st f t dt, which is fs, small f of s, and I shall write this as small f of s, and the left side is L of f dash t, or therefore L of f dash t is equal to sfs minus f of 0. So this is the Laplace transform of first order derivative we have obtained. Now this result is for nth order derivative, Laplace transform of nth order derivative, and the right side is in this form. So the first term is s into f of s. See, if you put n is equal to 1, the result is now can be verified. So n is 1, that means first derivative of f, which is the left side, and n is 1, s power 1 is sfs, this first term, and n is 1, you see the last term, n is 1, 1 minus 1 is 0, means 0 derivative of f means no derivative, so only f of 0, so that is the last term. So first and last term is obtained, and middle term, see, or here you can put s is n is 1, so 1 minus 1, that is 0, s power 0, that is 1, f of 0. So only two terms exist for the first order derivatives Laplace transform, and now we can suppose this as 1. So from this we shall write the result, or actually what this means is fs means L of ft, so that is to be noted, or this can be stated as, therefore L of f dash of t is equal to s L of ft, capital F of t, minus f of 0. Now from this we can write the same result in terms of another function, that is in place of f I shall write the result in terms of g. So from this we can write L of g dash of t is equal to, I am replacing capital F by capital G, only notation is changed. So s, with this s will remain same, L of g of t minus g of 0. See, in place of f I have written g, so this result remains the same, the form is same. Now what we shall do is we shall put this g dash t is equal to f. So then or g of t is equal to f dash t, we shall write. Now take g of t is equal to f of t, not f of t but f dash of t. We can take this function in this result. Now forget about this and consider g of t is equal to f dash t in this result. So this result becomes, then we get in this, we get, now see what we shall get. gt is f dash t, so therefore what will be g dash t? G dash t means derivative of this on both sides, differentiate, this will be f double dash of t, and this becomes L of f double dash of t. we get L second order derivative of f, and right side is L s L of gt. G of t is f dash of t. See this, f dash of t minus g0, g of 0, that is put t is equal to 0 here, f dash of 0 minus f dash of 0. So this we have obtained. Now you see here it is the term L. So this procedure is simple. See, first we have obtained this result, then this result is written in the form of G. In place of f we have written capital G. Again we are putting capital G as f dash of t. This is consideration, and then this result, this is G dash t, or here therefore G dash of t is equal to f double dash of t, taking derivative on either side, and this G dash of t is put as f double dash of t. Right side is s L, G of t is f dash of t minus g0, g0 is f dash 0. Now we use the first relation, first equation here, L of f dash t we have obtained earlier, put it here. So using 1, this is equal to, therefore L of second order derivative of f is equal to s into bracket, this is s in bracket sfs, L of f dash of t we are writing sfs minus f0 minus, yes, this much is written here in bracket, minus this term f dash of 0 same by 1, or using 1. And now you see this is equal to s into s, that is s square fs minus s f0, s capital F of 0 minus f dash of 0. So this is what we have obtained is L f double dash, Laplace transform of second order derivative, and we shall assume this result as second. Now you see this result is obtained as the second result. Now this can be verified whether it satisfies the given result or not. If you put n is equal to 2, the left side is L second order derivative of f, and right side is, see, n is 2, s square f of small f of s minus, again n is 2 minus 1, that is s f of 0 minus n is 2 minus 2, that is 0. So s power 0 is 1 and f dash of 0. So here the last term is only in terms of f, capital F dash, or derivative of capital F, and that is the last term. So therefore this is verified, the result verified, and continuing like this, this can be generalized, or one more step we can do, and that is, now we write this same result in terms of h function, capital H. So from this we can write in the second result we shall replace again as earlier, here we have replaced f by g, in that result we shall replace f by h. So from this result we can write L of h double dash, or means second order derivative of h, is equal to s square. So this is fs, means L of f of t, fs is L of f of t, see, and therefore here the function is h, so that will be L of h of t minus s, in place of f it is h, h0, h at 0 minus h dash 0. So this is the result we have obtained by replacing f by h. Now we write taking h, see here we have taken g is equal to f dash, Now here I shall take h of t is equal to f dash of t. We get, taking in this result, we get. Now see, h of t is f dash of t. So what will be second order derivative of h? Will be third order derivative of f, differentiating 2 times either side. So that will be third order derivative of f. So in this result we shall write that is L of second order derivative of h will be third order derivative of f at t is equal to s square L of h of t is f dash of t minus s h at 0 means f dash at 0 and minus h dash at 0 will be f double dash h dash f double dash at 0. See, this we shall obtain. You see the steps here. H of t is taken as f dash of t and accordingly we have changed the terms. Now again we use this value from 1 L of f dash of t and write this expression here. So that is equal to s square in bracket SFS, L of f dash t is SFS minus capital F at 0 minus S f dash at 0 minus second order derivative of f at 0. So this we have obtained and we may write by 1. Or finally the Laplace transform of third order derivative will be, or therefore L of third order derivatives Laplace transform is equal to s in s square into s, that is s cube f of s small f of s minus s square f capital F at 0 minus the same s f dash at 0 minus f double dash at 0. See, this is the result we have obtained for Laplace transform of third order derivative, and so on. This can be now continued. See, we have L of f dash of t is s fs minus f of 0. L of f double dash of t is s square fs minus s f 0 minus f dash of 0, and L of third order derivative of f is s cube f of s minus s square f 0 minus s f dash 0 minus second order derivative of f at 0. So that means here the order of derivative is third, so the term starts with the third power of s. Then this is fixed as small f of s, and then the power of s small s decreases by 1. This is s square, then s, and last is no power of s, that is s power 0 is 1. So last term does not contain s, and that means in decreasing order, and thus in general we shall get the result by taking nth derivative n here, nth derivative of f, and its Laplace transform of nth derivative of f is s power n f of s minus s power n minus 1 f 0 minus s power n minus 2. See, the power of s is decreasing by 1, and then here the first term is small f of s, then the term starts with capital F 0, then the order of the derivative goes on increasing, and in each term this order plus n the power of s is n minus 1. So here 0 order n minus 1, here power of s is 1 and n minus second derivative means the sum of these two is n minus 1 from this term onwards, and thus here if you put n is equal to 3 we shall get the same result, and so on. And so on, we shall get generalizing this, we get the required result. Generalizing this, we get the required result. So thus we have obtained the required result, and this proves the theorem. So this result is the general result, and we should remember it. But this is important, also important in application of Laplace transform when we solve differential equations. So what is the first result we have earlier written in earlier step, and that was, I shall write here, that was Laplace transform of f dash of t is equal to s f of s minus capital F at 0. So this is also to be remembered. This is the Laplace transform of first order derivative, and this is the Laplace transform of second order derivative. So, and this is the Laplace transform of third order derivative, and this is the Laplace transform of nth order derivative. So in this way we have proved, actually the result is proved by induction, we have proved, and by observing the terms, and we have generalized it to get the result. So this proves the theorem for Laplace transform of derivatives. Now how to use it? So one use, I told you that this is useful in application of Laplace transform to solve differential equation. We take the Laplace transform of derivatives, second order derivative, third order derivative will be there in differential equation, and that is useful. But in problems also, problem can also be solved by using this result. Now we shall have a problem here. See, if the Laplace transform of say root t is equal to, and this is, you can use the formula also, t power half, it is root pi, the Laplace transform of root t is, you can check it, 2s power 3 by 2. Then find, or given Laplace transform of this, find, you can say given, instead of f, given L of root t is this one, find Laplace transform of 1 by root t. So why this problem is considered? Because this for this evaluation of this Laplace transform, we can apply the theorem on Laplace transform of derivative, because these functions can be expressed in terms of derivative of each other. So we can take this as f of t. See, L of f of t is fs, that must be first obtained, and then using that we can obtain the Laplace transform of derivative, first order, second order, third order, etc. So first of all we shall consider in the solution that let f of t, capital F of t is equal to root t. Then L of root t, that is given, this is, then L of f of t is equal to f of s, and that is given. So that is L of root t is root pi divided by 2 into s to the power 3 by 2. It is given. We can assume this as 1. Now what is f dash of t? See, f dash of t, f of t is root t. What will be f dash of t? Derivative of root t. Now f dash of t is equal to derivative of root t, d by dt of root t. And we know the derivative of root t is 1 over 2 root t. This is, so that means 1 by root t is the function in f dash of t. Half is constant, that can be adjusted, can be written outside the Laplace transform, but the form is 1 by root t. And now we use this result. We have Laplace transform of f dash of t is equal to, by theorem 6, Laplace transform of f dash of t is s into f of s minus f of 0, capital F of 0. and therefore L of what is f dash of t, this is 1 over 2 root t, and is equal to s. What is fs? Fs is here, you see, it is given L of root t, that is f of small f of s, and root pi divided by, it is root pi divided by 2 into s to the power 3 by 2 minus f of 0. So what is f of 0? It is easy. Put here t is equal to 0. F of 0 is root of 0, and root of 0 is 0. So this we have written by 1 using this, and also f of 0 is 0. So thus now you see, for this 1 by 2 can be taken outside the Laplace transform by linearity property. We know it is a constant. Constants can be written outside the Laplace transform. So Laplace transform of 1 upon root t, and this is equal to, now you see, this half can also be taken separate, and s we can take at the denominator with negative power, or this term of s cancels from these two, and we get root pi divided by s to the power 3 by 2 minus 1, that is 1 by 2. So this is the expression now, and half can be divided out from both sides or multiply both sides by 2. So that this gives Laplace transform of 1 by root t is equal to root pi divided by s to the power half. So this is the result that we want to find out, Laplace transform of 1 upon root t. Now we can verify both the results. So why this problem is taken? Because of how to use this result, Laplace transform of derivative. For that purpose we have taken this problem. But see, without using the problem, that can be verified directly. So we have the formula, Laplace transform of t power n. See, Laplace transform of t power n is gamma of n plus 1 divided by s to the power n plus 1. Now see, t 1 by root t means Laplace transform of t to the power negative half. This is, and that will be gamma of negative half plus 1 divided by s to the power negative half plus 1 is c1 half. And what is negative half plus 1? That is 1 half, and gamma of 1 half is root pi. So root pi divided by s to the power half. So that is verified. This can be, this is written for verification. But how to use the theorem? To understand that, there we have this problem. Now one problem you should solve yourself, and that is, see, it's a problem for practice. See, if given Laplace transform of cos 3 by 2 t, this is say 4s divided by 4s square plus 9. We can verify this. Find, given this, find or show that Laplace transform of sine 3 by 2 times t is equal to 6 divided by 4s square plus 9. So this is the answer actually. And now you can solve the problem as in the same way. We should take this as f of t, and what should be this? The derivative of cosine is sine. So actually negative sign and constants will be there, but negative sign and constant can be written outside the Laplace transform, and therefore this result is applicable for obtaining this Laplace transform of sine 3 by 2, and you can solve this problem as like the earlier. So take this function as f of t, write f dash of t. What will be f of 0? The cos of 0, that will be 1 here, that is to be noted. And then write this result, put the both side the values. Value of fs is this one, and f of 0 is 1, and then simplify, eliminate the constants on either side, you will get this result. So this is about the theorem on Laplace transform of derivatives. So one more theorem is a similar theorem is there, but we will consider or take that theorem in our next lecture, which is a derivative of which is Laplace transform of integral, that we will have in our next lecture. Thank you.